You wouldn't sail a ship without a compass. So why would you inspect steel without the right ultrasonic tools? In the world of structural integrity, precision isn't just a luxury, it's a necessity. Today, we're unpacking the instruments that make ultrasonic thickness testing not only possible, but accurate, reliable, and repeatable. Whether you're in the dry dock or 50 meters underwater, ultrasonic testing isn't just about sending waves through metal and reading numbers on a screen. It's the marriage of precise instruments, skilled hands, and a deep understanding of your environment. The right probe, the right gauge, the right calibration block. These aren't just accessories. They're your lifeline to the truth about steel, welds, and structures that people trust with their lives. Let's get tactile. Let's talk about the gear that makes UT work in the real world. Every structure you inspect is different. A thick ship hull isn't the same as a thin riser clamp. An underwater pipeline doesn't behave like a surface weld plate. The wrong probe, the wrong frequency, the wrong surface. And your data is as unreliable as a compass that points west. The right tool ensures your readings are accurate, your results are trusted, and your integrity reports leave no room for doubt. Let's begin with the beating heart of the ultrasonic system, the probe. The probe, sometimes called the transducer, is where science meets steel. This device is responsible for both sending and receiving ultrasonic signals. It's the first point of contact, the sensor that bridges the gap between theory and reality. There are two main types of probes you'll encounter in ultrasonic thickness testing. First, the single crystal or single element probe. This probe uses one piezoelectric crystal to generate and detect sound waves. It's the workhorse of straight beam thickness gauges, the tool you'll see in most routine inspections. If you're measuring the wall thickness of a flat plate or a slightly curved pipe, the single crystal probe is your go-to. Simple, reliable, and repeatable. But what if your surface isn't pristine? What if there's corrosion, pitting, or marine growth? That's where the twin crystal or dual element probe shines. This design features two separate crystals, one for sending, one for receiving. By separating the transmitting and receiving functions, twin crystal probes minimize the so-called dead zone near the surface, giving you accurate readings even at close range. They excel on rough, corroded, or coated surfaces and are indispensable for underwater applications. If you ask any diver who's done a wall thickness survey at depth, they'll tell you, twin probes are the gold standard for high attenuation materials where signal loss can make or break a job. But the world of probes doesn't stop there. Specialized probes take ultrasonic testing further, adapting to the unique challenges of each inspection environment. Angle beam probes, for instance, send waves at precise angles, allowing you to detect flaws in welds using shear waves, a critical technique for weld integrity inspections. Miniature or fingertip probes are built for tight spots and complex geometries, squeezing into places larger probes can't reach. High-frequency probes are tuned to detect the smallest flaws, making them ideal for thin materials or high-resolution inspections. On the other end of the spectrum, low-frequency probes penetrate deep into thick walls, sacrificing detail for reach. Choosing the right probe is both science and art. Frequency, diameter, element configuration, and even the probe's casing can all influence your results. In the end, your probe is your first line of truth. Choose wisely, and your data will speak for itself. But a probe alone isn't enough. Once you've chosen your transducer, you need a way to interpret the returning echoes. That's where the thickness gauge comes in, the interface between you and the steel. Basic digital thickness gauges are the foot soldiers of the UT world. Rugged, lightweight, and designed for field use, they feature a simple interface. Press the probe to the surface, and you get a number. These devices are perfect for quick checks, corrosion surveys, and routine thickness measurements. Their simplicity belies their importance. In the hands of a trained technician, even a basic gauge can reveal critical information about structural health. But sometimes you need more than a number. That's where A-scan display units come in. Think of the A-scan as a real-time ultrasound of steel. Instead of giving you a single value, the A-scan displays a waveform, each echo visible as a peak on the screen. This visual feedback allows inspectors to see multiple echoes, verify wall thickness, detect back wall dropouts, and even identify internal flaws that might otherwise go unnoticed. With an A scan, you're not just reading data, you're interpreting it, understanding it, and making informed decisions. A good thickness gauge isn't just about display, it's about functions. Velocity calibration allows you to adjust for different materials. The speed of sound varies in steel, aluminum, and composites, so your gauge must be calibrated to match. Gain settings amplify weak signals, ensuring you don't miss critical echoes in noisy environments. Data logging capabilities let you store thousands of readings, making large-scale surveys manageable and traceable. Alarm limits flag thin spots instantly, alerting you to areas that require immediate attention. Your gauge is your translator. It takes the language of echoes and converts it into something you can trust. A measurement, a diagnosis, a decision. But all of this, probes, gauges, settings, means nothing without calibration. Even the best equipment must be checked against a standard. That's where calibration blocks come in, the gold standard of accuracy in ultrasonic testing. Calibration blocks are precisely machined reference pieces, typically made from the same material as the test object. Their job is simple: provide a known reference so your equipment can be tuned to deliver accurate results in the field. One of the most common calibration tools is the step, or wedge, block. These blocks feature a series of steps, each with a known thickness, such as 2 mm, 4 mm, 6 mm, and so on. By measuring each step and comparing the readings to the known dimensions, inspectors calibrate their gauges, ensuring the time it takes for a sound wave to travel through steel is correctly translated into a thickness. For angle beam probes, calibration requires something more sophisticated. Enter the V1 and V2 blocks, specially designed for shear wave calibration. These blocks include features like flat bottom holes, radius notches, and reference surfaces, enabling precise calibration of probe angles and sensitivity. Without them, flaw detection in welds would be little more than educated guesswork. But sometimes standard isn't enough. In the field, you encounter pipelines with complex curves, plates with coatings, and structures that defy generic standards. That's where custom calibration blocks come into play. Machined to mimic the geometry and material of the actual structure, these blocks ensure your calibration is as close to reality as possible. In environments where a millimeter can mean the difference between safety and failure, custom calibration is non-negotiable. Calibrating with the wrong block is like weighing yourself on a broken scale. The numbers might look right, but they tell you nothing about the truth. Now, let's take a dive, literally. What happens when ultrasonic thickness testing goes underwater? The challenges multiply: increased pressure, changing temperatures, limited visibility, and the ever-present movement of water. Underwater inspection gear is built for this pressure, both literal and metaphorical. Waterproof Ute units are designed with glove-friendly buttons, allowing divers to operate them in cold, murky conditions. Large, backlit displays provide visibility, even when sunlight can't reach. Transducers are connected by heavy-duty cables, and probes are designed to withstand both the elements and the rigors of subsea work. In many underwater inspections, the water itself becomes your coolant, transmitting ultrasonic waves between probe and steel. Heavy-duty twin crystal probes are the tool of choice, able to handle the signal loss that comes with high attenuation materials and the unpredictable nature of the ocean environment. For real-time monitoring, surface-deployed digital readout units allow topside teams to see what's happening below, ensuring critical decisions are made with the best possible data. In the underwater world, precision is everything. Every reading could be the difference between a structure's success and catastrophic failure. So what does all this mean for you? The inspector, the engineer, the diver, the decision maker? You can't fake a measurement. You can't guess a flaw. Whether you're inspecting the hull of a ship, the riser on an offshore platform, the beams beneath a bridge, or the pipes in a refinery, your probe, gauge, and calibration block must fit the job. Know what you're testing. Know how deep you need to go. Know what type of flaw you're looking for. Because in ultrasonic testing, your tools define your truth. The wrong tool can mean missed corrosion, undetected cracks, or false confidence in a structure that's anything but sound. Every seasoned inspector will tell you, UT is as much about preparation as it is about execution. Before you take your first reading, you've already made dozens of decisions: which probe, which frequency, which gauge, which calibration block. Each choice brings you closer to a result you can trust or further away from the truth. Imagine you're on a platform in the North Sea, tasked with verifying the integrity of a critical pipeline. The steel is thick, coated with decades of marine growth, and the sea is anything but calm. You reach for your twin crystal probe. Its design minimizes the dead zone and compensates for signal loss. You connect it to a robust waterproof gauge with a large backlit display. You calibrate against a custom block machined from the same alloy as the pipeline, ensuring your readings are as accurate as possible. You lower yourself into the water, the current tugging at your suit, your gloves thick and clumsy. But your equipment is designed for this. Glove-friendly buttons, cable-secured probes, and a display you can read even in the gloom. Each reading you take isn't just a number. It's a decision, a responsibility, a testament to the power of the right tool in the right hands. Back on the surface, your data is logged, reviewed, and trusted. The client knows their structure is safe. The crew sleeps a little easier. The operation continues, not because of luck, but because of preparation. This is the reality of ultrasonic thickness testing. The tools aren't just gadgets. They're your connection to the materials and structures that shape our world. They turn invisible flaws into visible data. They transform uncertainty into confidence. They allow you to stand behind your work, knowing that every reading is as true as the steel beneath your feet. In our next exploration, we'll move beyond the tools and dive into the technique itself. How do you perform ultrasonic thickness inspection correctly, step by step, in the field? From preparing the surface and choosing the right couplant, to positioning your probe, setting the gain, and recording measurements the right way, every step matters. For now, remember, like a compass to a sailor, your UT tools are your guide. They point you towards safety, reliability, and structural integrity. The right tool is always the right call. If you found this helpful, share it with someone building their UT skill set. Like, comment, and join us as we continue to explore the world of ultrasonic testing. This is Understanding UT, and we're just getting started.